a way of saying, you know, let the mathematicians do the math, let us figure out what they really want to describe with them. And this is what I want to explain to you. And I want to explain to you the underlying principles of spectroscopy. The information of spectroscopy is there because the spins interact with something. I mean, the first interaction of what the spins do, the magnetization doesn't interact with the magnetic field. This is why we can observe NMR in the first place. But then they also interact with each other. There's a spin-spin interaction, which gives rise to the J coupling, as the chemists know very well. But we also have a coupling through space, which we call the dipole-dipole interaction, which really makes solid-state NMR so difficult. This is why we use magic angle spinning. So once we understand a little bit about the spin couplings, we learn how to read NMR spectra, and we know why we have to do magic angle spinning if we want to do solid-state. So why I want to, you know, put the burden on you of going through this somewhat complicated chapter is that you at least get an appreciation for these reasons and the underlying physics behind it. And the first part is that we want to understand what does coupling mean. And this is just the part sort of how a mathematician looks at coupling. I mean oh yeah, I have to put that up here. We look at spins. There's the spin, okay? The spin is nothing but an angular momentum that relates, is proportional to a magnetic dipole. That's what this equation says. There's an angular momentum, and the angular momentum is quantum mechanical, so it's a spin vector, and there is Planck's constant and the gyromagnetic ratio. So it has the spin is proportional to a magnetic moment, something we've discussed before. So it's a vector. A vector means it's a quantity that is oriented in space. You can rotate it, like a finger of a clock. So it has an orientation. It has a magnitude and a direction. So a vector typically in space has three components. Here's a vector, okay? So it has three components that everybody knows. Now, if a quantity couples, interacts, you interact with somebody, you need an interaction partner. So it's two. Minimum is two for an interaction. Now the question is, how does a mathematician describe an interaction? An interaction is described in terms of a multiplication, a product. Now a vector can interact with a scalar or with another vector. Typically it's a vector interacts with a vector. Equal, similar quantities interact with each other. So you have to describe the interaction of a vector with a vector. So two quantities that have a magnitude and a direction. And that is the general form of interaction is described by multiplication of the spin here, and the vector is the interaction partner, and that describes the type of interaction. It's a coupling mechanism. And the coupling mechanism is described by a matrix. So I hope, how many still know how to multiply a vector with a matrix? Chemists? Yes, you do? Okay, cool. My chemists don't know. I usually have to explain in detail. So, here's a matrix, a 3x3 matrix. And what you do is you take that vector, flip it over here, and multiply these pairwise and add them, right? And then you do the same thing and multiply this one here with this matrix, and as a result you get a number. And that number is an energy. It's the interaction energy. How strong do you interact? Big energy, weak interaction, small energy. That's all there is. Now we have to figure out what type of interactions can a spin have. And the interactions a spin can have is what we call the Zeeman interactions, and the spin, this is the spin, interacts with the magnetic field. There's a chemical shift, this is the applied field. The chemical shift, which we want to measure in chemistry, that is the interaction of the spins with the magnetic field produced by the electrons surrounding the nucleus, the shield. Then we have the radio frequency excitation. We have to have an interaction of the spins with the applied radio frequency field, otherwise we couldn't do a 90-degree pulse. We have a quadrupole interaction, which comes in for certain nuclei that have a spin quantum number larger than 1/2. And then we have the dipole-dipole interaction. We take two magnets through space, and when you put two magnets close to each other, you feel either attraction or repulsion, depending on what their orientation is. And there's a third type, the last type of interaction is the indirect coupling. Again, you have two spins, but now they're connected by chemical bonds. And the magnetization of that spin polarizes the electron orbitals through the chemical bonds, and that spin senses through the chemical bonds the orientation of that spin. It's called the indirect spin-spin coupling. So we have the indirect coupling through the chemical bond, the direct coupling, the dipole-dipole interaction. And here I've given rough numbers, very crude numbers of how strong these interactions are. And the strongest interaction is a Zeeman interaction. This is for a 100 megahertz spectrometer. Hardly anybody uses it anymore today. This is an old-fashioned chemical shift, maybe 10 kilohertz, depends on field strength and nucleus. Radio frequency excitation, 100 kilohertz, pretty strong radio frequency field here. Quadrupole interaction could be 10 megahertz, very strong, very difficult to measure quadrupole nuclei. Dipole-dipole interaction for protons and solids, 50 kilohertz, sometimes 100 kilohertz. Makes life very complicated. And the indirect coupling, 5 hertz. Weak, maybe 10 hertz. Very weak, very small. Again, hard to measure if you don't have a good instrument. So these are the interactions we have to deal with, but I see that my time is up, so I cannot go through those. But examples that we will address next time is we start with the dipole-dipole interaction, and we will learn that these interactions are anisotropic, which means they depend on the orientation of the molecule in the magnetic field. And in liquids that doesn't play a role because the molecules move so fast that the NMR can only see the average of the molecule it sets. It doesn't see the orientation. But in solids, the orientation plays a role. And that is a blessing and a pain. It's a blessing because we learn about the orientational distribution of, let's say, chemical groups in spun fibers, how well are the molecules aligned in the fiber. And it's a pain because the dipole-dipole interaction is there and spoils our NMR signal. So we have to learn how to live with it, and we will talk about this next time. Any questions? No? Maybe when the camera is off? Thank you.
For the second course, those who are participating in the second course should come at 2 o'clock. 2 o'clock you should be here.